Right, so here's the video for Algebra 2, first one we've done this year. I'm going to have all the information that I saw from us meeting together in person, but also the stuff you guys have submitted to me, stuff I think we need to work on. It's not a ton, which is why I'm just going to make it into one video and send it to all you guys. So let's get into it. First things first, I want to talk about some basics, right? This is one of the things I saw a couple people get tripped up on. Let me turn up brightness a little bit. One of the things I saw people get tripped up on was this. They'd have a problem like 5 times 9 squared, and they would say that this means 45 squared. And first off, it does not mean that. So this sign right here means not equal. That is not true. What it does equal is 5 times, this means 9 times itself. 9 times 9. And if you notice, that's not 45 times 45, it's 45 times 9, right? So one way of getting around this is thinking PEMDAS, exponents comes before multiplication, and so we have to figure out what this is. But the way I think of it is I just think this means 5 times 9 times 9. I would never say 45 times 45, right? Think about what it means, and you won't make this mistake. So 45 times 9 is what we're doing. The way I would do that in my head is 45 times 10, I know is 450. So 45 times 9 is just 1 less 45. So it looks like 405 to me. I also want to talk about reciprocals and negative exponents. So to remind you all, I know I've done this like a million times now, but it's just starting to sink in for some of you, and some of you still have some questions. If I have negative exponents, so like 3 cubed means 3 times 3 times 3. 3 to the second is 3 times 3. 3 to the first is 3. 3 to the 0th, we know has to be 1. We've talked about this, and I think a lot of you guys are starting to get this. Because as we go up, like if I were to go up one more, like 3 to the 4th, as the exponent goes up, it's repeated multiplication, right? That means 3 times itself 4 times. So basically it's 3 cubed, but we're timesing on another 3, right? Because we've gone up. If we go down, that means from like here to here. Notice I've gotten rid of a 3 to get there. And so what's happening is I'm dividing out of 3. So every time I divide out of 3, I get to the next level below. So if I divide out of 3, that 3 goes away, it becomes a 3. And if I divide this by 3, I get 1. So it's not going to be 0 here, because as we go down, we divide out of 3. 3 divided by 3 is 1. 1 times 3 times 3 is 3 times 3. Divide these 3's, I get 1. 1 times 3 is 3. As I go down, I'm dividing by 3. 3 divided by 3 is 1, not 0. If I do that again, then I've got 3 to the negative first, following my pattern, and the answer will be 1/3. So multiplication can be repeated again and again with exponents, right? Just like addition can be repeated again and again with multiplication, right? If I do 3 times 5, it means 3 plus 3 plus 3 plus 3 plus 3 5 times, right? 3 to the 5th then would be 3 times itself 5 times. When we use negative exponents, it's really not going to make it negative if it didn't start negative, right? 3 didn't start negative, so it's not going to end up being negative when I get to here or here or here, because negative exponents just mean repeated division. So if I start at 3 to the 0th and divide by 3, I get a 1/3. 3 to the negative second means take 1 and divide it by 3 2 times. If I divide it by 3 twice, I don't end up with 1/6. I end up with 1/9. And the reason for that is if I have 1/3, that's what this is, right? 1 out of 3 pieces. And I divide 1/3 by 3, I'll end up with 1/9. And if I divide 1/9 by 3, I won't end up with a 12th. I'll end up with 1/27. Notice that I'm never going to get to 0, or for that case, negative, because when you divide up something, it never really becomes like, it never becomes 0. It always just gets smaller and smaller. So if I take 1/9, that's what that is, and divide that by 3, then I've got 27ths. So that's one piece out of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 21, 22, 23, 24, 25, 26, 27. 27 of these guys is what I've got going on here. So 1/27th. And you might also notice a pattern 3 cubed is 27. 3 squared is 9. 3 to the first, of course, is 3. 3 to the fourth is 81. 9 times 9. 9 times 9. And you'll notice that negative exponents are basically the same thing as regular exponents, except the repeated division. Or you can think of it like reciprocals. 3 cubed is 27. 3 to the negative third is 1 over 27, or the reciprocal of 27. Same thing with 3 squared. It's 9, so 3 to the negative second is 1/9. They're reciprocals. So if I were to predict what 3 to the negative fourth would be, 3 to the fourth is 81, because 9 times 9 is 81. So 3 to the negative fourth is 1 divided by 3 divided by 3 divided by 3 divided by 3, or the reciprocal of 81. I want to talk about reciprocals and why they are important and why they do what they do. A reciprocal, by definition, let me write that out, reciprocal, by definition is this. If you have a number like 5 and you want to times it to get 1, the number you times 5 by to get 1 is called the reciprocal. So you have to figure out what that number is. Well, 5 times 0 is too small, because that would get us 0. And 5 times 1 gets us 5, so that's too big. So it's got to be between 0 and 1. And the number it's going to be is 1/5. And we know this because when we times by a fifth, we times by the top. 5 times 1 gets us 5. And then we divide by the bottom. 5 divided by 5 would be 1. Or we can divide by the bottom first. 5 divided by 5, 1. Times 1, 1. So 1/5 is the reciprocal of 5 because it multiplies to make 1. You'll also notice the pattern is that it's the flip of 5, right? Because if you think of 5 as a fraction, 5 over 1, when you flip that number, you get 1/5. So there is that pattern there of how reciprocals work. Now, the reason reciprocals are useful is because timesing by the reciprocal is the same thing as multiplying or dividing by the number. And that's super important because sometimes dividing by fractions is weird. Let me show you what I mean. If I had, let's do 10 divided by 2/3. Now, the idea is we want to think about how many times does 2/3 fit into 10? And you could do that if you wanted to, right? There is a way to think about that, right? If I had 2/3 once, that's 2/3. 2/3 twice is 4/3. 2/3 3 times is 6/3, so that's 2, right? And I could do that 5 more times to figure out how many times this goes in. But that's kind of hard to think about. And so instead of dividing by 2/3, what we can do instead is take 10. This is the exact same thing as 10 times 3/2, the reciprocal of 2/3. And the reason this works is this. If I look at the reciprocal of 5 and I multiply them together, I get 1. If I think about division, what number do I divide 5 by to get 1? Well, of course, 5 divided by 5 is 1. So it looks like what we've just proven is that 5 times 1/5 is the same thing as 5 divided by 5. Because again, 5 times 1/5 is 1, and 5 divided by 5 is 1, so that means these must be equal. Well, we already know 5s are equal, so apparently what must be true is that timesing by a fifth is the same thing as dividing by 5. Or as we talked about earlier, 5 over 1, the reciprocal. Same thing with this. If I were to take, let's do 7. If I multiply by its reciprocal, 1/7, I get 1. So that must be the same thing as dividing by 7. Because of course that gets 1 as well. So in other words, timesing by a 7th is the same thing as dividing by 7. This is the same as that. And it makes sense, right? Times by 1, then divide by 7 will be the same thing as divide by 7. Times by 1, divide by 5 is the same thing as dividing by 5. So here, instead of dividing by 2/3, I can think of it as timesing by 3/2, the reciprocal of 2/3. If I do that, it's much easier to do the math in my head. I times by the top, divide by the bottom. Looks like 30 divided by 2, or 15. Or if I wanted, divide first. 5. 10 divided by 2 is 5. Times 3 is 15. This will be the exact same answer. 2/3 fits into 10, 15 times. So reciprocals are super powerful, and that's why. Timesing by a seventh is the same thing as dividing by 7. So timesing by 3/2 is the same thing as dividing by 2/3. And it's often easier to think of multiplication than it is division. I think the last thing I want to talk about for Algebra 2 is this. Is that really the last thing? Last two things, technically. I want to talk about common denominators. A lot of you guys get tripped up on 4.2.1, so let's find that. Here's section 4.1. If I skip down to the bottom, we'll have the exercises for it, and then beginning of 4.2 is right here. So let's find the exercises in 4.2. If I go past all the problems and their examples, eventually I'll get to the exercises. There we are. And 4.2.1 part D is the part I think a lot of people are getting screwed up by. So that part D, or not part D, where is it? C and D. C and D are the ones that are getting screwed up by. And the hard part about C is not the 3c squared and the 5c squared. Let me write that out. Whoops, that's a 2. Let me copy this down and then we'll switch. Minus 7d squared plus 5c squared. All right, let's take a look at this. So the hard part isn't this and this, because those are like terms. They're both c squareds. I have 3 of them. I'm adding 5 of them. How many total c squareds will I have? I'll have a total of 8 c squareds, and it's not c to the 4th, because remember, c to the 4th is c times c times c times c, and we're not timesing here. We're adding. So 3 of them plus 5 of them is 8 of them, 8 c squareds. The hard part for people tends to be combining these like terms. They're both d squareds, and that's a 2, by the way. And there are 2 ways to handle this. Option 1. Here's the part that's confusing us. Option 1. Since there's no equal sign, we can't multiply both sides by 2 to get rid of the division. If there aren't both sides, right? There's no equal sign here to multiply both sides. But what we can do is we can multiply everything here by this. So basically what we're doing is we're timesing everything by 2. That's going to get us this. 2's divide out, I get d squared. 2 times negative 7 is 14. And because we doubled everything, that changes the problem, right? The way we don't change the problem normally is we do it to both sides because there's an equation. But since there's no equal sign, we've just doubled it and it's straight up a different problem. So we're not solving the problem they want us to solve. However, if we times by this, remember that means divide everything by 2, we can divide everything by 2 later. And so if I double it and then divide it by 2 later, it is the same thing, it's just a different way of looking at it. And once I'm like this, I can see 1 of them minus 14 of them is negative 13 of them. In this case, negative 13 d squareds. So that's what number is going to go here, along with our 8c squared. That's how you combine these two. The other option is to get common denominators, which turns out is the exact same thing. So let's talk about the hard part. Again, it's this part. If I think to myself, how do I make that into halves so that their denominators will be alike? Because right now it's 7 over 1, right? How do I make this number into halves? In other words, we need to think, how many halves are in 7? And there's 14 halves in 7. And you can check that because 14 divided by 2 is 7. So I didn't change it. I've got d squared over 2, right? Minus, and then instead of 7d squared, I just have 14 divided by 2d squared. And of course, 14 divided by 2 is the same thing as 7. A way you've probably seen this before is you'll have somebody multiply by 2 over 2. And the reason we don't need to do this to both sides or anything crazy is because 2 over 2 is just timesing by 1. And of course, timesing by 1 doesn't change the number. 7 times the top is 14, divided by the bottom is 14 over 2. So I'm getting common denominators. That's how I knew to multiply by 2 over 2. I wanted a 2 in the bottom, so I multiplied by 2 over 2 to get there. Typically, how I just think is, okay, I want this to be halves. How many halves are in 7? And now, whoops. 1d squared over 2 minus 14 over 2d squared. 1 minus 14 is negative 13 over 2d squared. There's a 1 here. I also want to point out that this is the same thing as this, with the d squared on top versus on the side, exact same idea. So I have 1 of them minus 14 of them. I'm left with negative 13 halves d squared. So your answer could look like this, plus that 8c squared that we had from earlier, or it could look like this, with the last possibility being this. Because notice that 2 would divide both, right? We get negative 13 halves, and we get 8c squared. All right, cool. So that's it for this week. Hope this was helpful. Hope you skipped around a bunch to figure out what was good for you. If you found a spot that was helpful for you, I would write down the video and the timestamp of like when we talked about that topic and write that in your notes. So if at like the 14-minute mark, we started talking about something that made sense to you, I'd write down the 14-minute mark. That way, if you want to, you can go back and find that video and the timestamp and know exactly where to get some help. Anyway, see you this week.